Hello, my name is McKenna Croft, and this is my Lab 2 report on the motion of a falling object. So the purpose of this lab was to determine the effect of gravitational forces and drag forces on an object that is dropped from rest by analyzing observed and computational models and applying fundamental physics principles. One of these principles is Newton's second law of motion. Which relates to the idea that all existing forces are not balanced and states that the acceleration of an object is produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and is inversely proportional to the mass of the object. It can also be translated to the momentum principle, which concludes the net force is equal to the change in momentum over the change in time. The velocity and position update formulas derived from Newton's second law are also used for iteration of the fundamental principle to find accurate position and velocity data over time. The forces analyzed in this experiment are gravitational force and drag force. Gravitational force is dependent on the mass of the object, the acceleration due to gravity, and the j-hat unit vector. The magnitude of the gravitational force is described by the equation here that's influenced by the magnitude of the position vector. Drag force or air resistance is the force of an object by a fluid to resist motion through it, which is impacted by airflow and object properties such as shape and size. Drag force is opposite to the direction of motion and is equal to the magnitude of the force times its unit vector. The magnitude is related to the constant b and the magnitude of the velocity. Overall, drag force is proportional to negative b times velocity. So a preview of the results, I found that the computational model that accounts for both the drag force and the gravitational force is a better estimation of the observed path of motion than the computational model that only accounts for gravity. So initial conditions and model assumptions, some were the motion is only along the y-axis. The force of gravity is the only force acting on the paper ball. The drag force is always opposite to the direction of motion, and its magnitude is proportional to the square of the ball's speed. And contrary to the previous lab, the net force is not equal to zero, as well as the change in velocity. So the system is a ball composed of notebook paper, and the surroundings are the door and the ground. Some initialization features: the mass of the ball was 0.0045 kilograms. And the acceleration due to gravity was set at 9.81, and j-hat was set at 0.10. Initial position vector and velocity vector were set at 0 because the ball started at rest, and the start time was 0 seconds, and the while loop was set to less than the final time, which was 0.700 seconds. Delta t was a small number, 100 times smaller than the final time, so approximately 0.001, and position and velocity formulas were updated to reflect Newton's second law. Force. The while loop net force changes are highlighted here, and when we run the code, we see a model with an orange arrow depicting the force of gravity in a position and time graph that looks similar to the observed motion on tracker. And this observed motion is shown here. In comparison, when the program is run with drag force equations highlighted here, the position and time graph also looks similar to the observed motion, and there is a blue arrow that signifies the drag moving in the positive y direction and the gravitational forces in the opposite direction in the model. Results show the gravity computational model underestimates the change in position of the observed position change after 0.067 seconds because the total force on the paper ball is impacted by only the gravitational force pushing the paper ball towards the Earth in the negative y direction. In contrast, the gravity and drag computational model is a better prediction of the change in position of the observed model due to the impact of the drag force where the constant b acts in the positive y direction. Since b is estimated correctly, both the observed and computational models for drag and gravity end at the same position. Both models show deviations in the position after 0.2 seconds and underestimate the position of the paper ball. The computational model for gravity and drag overestimates at the end of the time frame, but the difference in position begins to decrease after 0.467 seconds. Some potential sources of error are inaccuracy of the center of mass at the point of the ball and tracker, modeling not accounting for motion in other directions than y, the drag coefficient not being precisely calculated, recording angle which could have been tilted, and the time scale of the video not capturing the motion of the ball appropriately. So some discussion questions. Which model predicts terminal velocity? The computational model that considers drag force predicts terminal velocity, which is exhibited by an asymptote present indicated by the change in slope between -2 and -2.5 meters per second, the velocity versus time graph. Thus, the net force of the paper ball would be 0 at terminal velocity because the air resistance or drag cancels out the force of gravity, balancing the forces. And if the paper ball was initially thrown downward, and the initial velocity was set at 0, -1, to signify this, in the computational model, the velocity versus time graph would reach terminal velocity at an earlier time, but the velocity at which the asymptote occurs is in the same velocity